let's see if, okay, I think it is okay now. Let me see, I have to connect it to QuickTime Player. There we go. Can you see it now?
Yes.
Excellent. Thank you very much. Sorry about that. I guess I forget that I have to log in through my school account to do the job. Okay, very good. So now let us just very briefly remember what we did last time. So we had two type of results about high dimensional space, in particular high dimensional, say, unit ball. First one says that if you consider a ball, right, and if you randomly pick a point, in all likelihood that point will be close to the surface because of the fact that by randomly choosing the vector coordinates using a normal distribution, we will be at a radius, the size of the vector will be square root d, some constant that depends on the variance of your Gaussian that you are using to generate the coordinates. So this is the first strange feature that tells us that most of the mass of the sphere is very near the surface. So that's one strange feature of high dimensional sphere. The second strange feature is that if you take the center of your sphere and if you cut it, so this is the, say, the equator, and we rotated it so that this is the direction of the north, right? And you cut it with two parallel hyperplanes, right? Because in high dimensional space, this would be of dimension d-1, right? And you do the same from the other side of the equator. Then the next strange thing is that most of the mass of the ball is in this slab between these two planes. Okay. So why are these two features so important for us? Well, for the following reason. The first feature tells you that if you are randomly generating vectors, in all likelihood, they are going to be of the same length, namely some constant factor times the square root of the dimension. So they will be approximately of the same size. That's the first. The other is, if you generate two vectors, say this is your first vector, and you rotate it so that it points towards the north, you rotate the whole sphere, right? Then in all likelihood, so the first property was due to the fact that most of the mass of the sphere is in this shell, or as it's called, Gaussian annulus, right around, it's a hollow sphere, right? The second strange property is that all of the mass, most of the mass is also near the equator, which means that if I randomly choose the second vector, it's going to, with all likelihood, belong to this slab around the equator. But what does this mean that it belongs to the slab around the equator? Well, this means if you look if you project to a, say, two-dimensional plane, and this is your first vector, the fact that the second vector is in this slab, it's essentially saying that if you project it, right, its orthogonal projection will be very small, i.e. it will be almost orthogonal, right? So this is then made a little bit more rigorous by two theorems. One is Gaussian annulus theorem that says that the probability, right? Probability that the length of your vector minus square root d, right, will be smaller by absolute value by epsilon of epsilon is sorry, not epsilon, let's call it beta to be consistent with what's in the notes. It's smaller than beta, with probability will be smaller than 3 times e to the minus beta squared times some constant c, which for the proof that we presented, actually, that you can read in the notes, c happens to be 1/96, but this can be improved, can be enlarged by more careful estimates. So this tells you, so what does this tell you? This tells you that you will differ here for more than beta, with the probability that is smaller, you will be outside of this annulus with probability that is smaller than this 3 times e to the minus c beta. And you can see now if beta increases, so if you allow thicker shell, a slightly thicker shell, this probability is going to get very quickly to 0, because e to the minus c times something large will be very quickly, will converge to 0, especially because beta is squared here. So this tells us in a more accurate analytic way, right? It tells us what's the probability that the length of your vectors will deviate more from square root of d. Now, the problem that I have is that my chat box has disappeared. And where could it be? Let's see. I need the chat box so that I can see what happened to it? My gosh. Okay, let me try if I go to Zoom and why did it go away? Oh, well. Oh. Show all windows. This should be, oh God, it's not. Okay, guys, I have to ask you, if you have questions, please, and don't be shy, unmute yourselves and tell me, and use your voice to ask questions. I cannot fight with this bloody software.
Hi, Alex.
Yes.
Can you hear me?
Yes, I can hear you.
Okay. I have a question about the hyperplanes around the equator.
About what?
The hyperplanes.
Yes.
So you said you randomly choose the first vector, then rotate it to face north. Wouldn't the planes also rotate?
Yeah. So so before putting these planes, just first, so we are choosing one vector, right, randomly. Then we rotate it to face north. This is not important. It's just to comply with the picture. And now you choose the second vector. A second vector is in this annulus that is, sorry, not annulus, this slab that is orthogonal to the first vector.
But if you rotate the whole sphere so the first vector is facing north, wouldn't the actual planes themselves also rotate?
Yeah. But the slabs are put, so you take the subspace that is orthogonal to that vector, and then do affine transformation, just shift it up and shift it down a little bit to produce this slab. But the slab is kept orthogonal to the first vector.
Like, so is the slab arbitrarily chosen then?
And so this is what we are getting to.
Okay.
So how do we choose this slab? Well, we proved the following theorem. We showed that if the thickness of this slab is C divided by 2 times C divided by square root of D minus 1, right? So C is a constant that we will vary, right, depending on the application. And clearly we consider C's that are all bigger than 0 and smaller than 1/2 square root of D minus 1 divided by 2 because of this. Clearly we want this, or actually it can be just smaller than square root of D minus 1. Because otherwise this distance will become 1. So you would be just touching the sphere here. So C is between 0 and square root of D minus 1, where D minus 1 is square root of the dimension minus 1. And the dimension in general will be of order of tens of 100 or 1,000. So C will be smaller or equal than say 100. So even if C is smaller than 100, then the theorem that we proved is this, that probability that you are outside of that slab, namely that you are here or here, is smaller or equal than, so probability of outside, right, is smaller or equal than 2 over C times e to the minus C squared divided by 2. So now you can see if C is, say, 100, or even if C is just 10, say you are in dimensionality 100,000, so square root of D minus 1 will be about 100. So say you take C to be 10, so that's just 10% of the total, the thickness is just 10% of the total diameter of the sphere. The volume that is outside will be smaller than 2 divided by 10. So this will be 1/5 of e to minus C squared divided by 2. C squared will be, if C is 10, this will be 100 divided by 2 is e to the minus 50, which is ridiculously small, right? So this shows that even for relatively modest size of cut, like you can take C to be, say, 4. So 4 times 4 is 16, divided by 2 is 8. E to the minus 8 is already extremely small, right? So the whole this mumbo jumbo is just to get to have precise, I mean, not precise, they are actually pretty sloppy, but good enough for all practical purposes estimates. So probability to be in the annulus is bounded by this expression where beta is half of the thickness of the annulus, right? Because it's on both sides of the sphere, you can deviate by a factor of beta. And this is how small the probability is to be outside of the annulus. And this probability is how likely you are to be outside of this, this slab, right? So the first one tells you how close you are to pick randomly a vector whose radius is exactly square root d. The other one tells you if you pick two vectors, how likely it is that they are not almost orthogonal, right? Because we saw that the orthogonal projection of this is, of course, smaller than beta, the length of the orthogonal projection. So, are you with me now? So this tells us, let me, oops. Okay, so this gives us this, and next thing that we want to do is, this is all what I just told you. Okay, so the next time is the next thing is to use this theorem, how it is used, this theorem. And then now we are actually going towards this idea of choosing a random coordinate system, so to speak, that is nearly orthogonal, orthonormal, and if we project vectors to this subspace. So you see, if you choose only two vectors, we saw what is the probability. But if you choose n vectors, of course, more and more vectors you choose, higher and higher will be the probability that one of them might misbehave, that it might go out of the annulus or out of the slab. So we want to see what estimates we can now derive if you have n points, if you choose independently and uniformly n points. And the estimates are these. So xi will be, of course, smaller than 1 because you are choosing randomly points that are inside the unit sphere. And we can show that with probability 1 minus 3/2 of 1 over n. So if n is large, if n is 10, for example, this probability is small, right? It decreases as 1 over n. If you have a guarantee that with this probability, so with high probability, the length of x will be larger than 1 minus 2 ln n divided by d. So n will be the number of points you choose randomly. So ln n will grow very slowly, and d will be gigantic because this is the number of dimensions. So in general, the number of points you choose is often actually smaller than the dimensions of the space. But in any case, this remains very small. This ratio remains very small because you take ln of the number of points, so that even if n is equal to the dimensions, if you choose very large number of vectors equal to the dimensions, this factor will remain small because ln n grows very slowly. So with very high probability, you will stay in the annulus, in the shell of this thickness, 2 ln divided by t. And your vectors will stay almost orthogonal, which means that the absolute value of your scalar product will be smaller or equal than square root of 6 ln n divided by d minus 1. So notice this will be small if n is, say, smaller than the dimensions, then ln n will be much smaller than the dimensions. And so this will be small. So this is essentially to say that every two vectors will be almost orthogonal, right? Because their scalar products are small. And the proof of this is very simple. If you take a unit sphere in dimension d and you reduce its radius for an epsilon, then the inner sphere will have its volume reduced by will have volume 1 minus epsilon divided by t times the original volume. And now we use the very useful inequality, namely the inequality, and I believe somewhere in the notes we have proved it. Inequality says that 1 minus epsilon is smaller than e to minus epsilon when epsilon is a small positive number, right?
Alex, I think, isn't it missing a 1, if I'm not mistaken? Shouldn't it be 1 minus e to the minus epsilon d?
Sorry, where?
So shouldn't there be a 1 in this equality? Because I think in the notes it has a 1.
You mean this, what I just wrote?
Yeah, so the 1 minus epsilon to the d is less than 1 minus epsilon.
No, in the notes is also, you see, this is 1 minus epsilon, and this is smaller than epsilon e to the minus epsilon, and then you take both powers to d. So this is, I think it's in the notes, the proof of that fact. It's a pretty simple proof. You can either use a Taylor formula, or you can use, you can bring e to the minus epsilon to the left-hand side, and then just argue by showing that it's a decreasing function and smaller than 0 at 0. So, right, because when epsilon is equal to 0, this is 1. And on the right-hand side, you also have 1. So you have that the statement is correct. And if you move this to this side of equation and you differentiate, you will get the derivative is negative, so it will be only decreasing. So 1 minus epsilon is actually smaller than e to the minus epsilon. And here we put both powers on d, where d is a dimension. And now we take for epsilon 2 ln n divided by d, and you get exactly what you need here. And here, when I replace epsilon with 2 ln n divided by d, d and d cancel out, and you get that this is e to the minus 2 ln n. Of course, 2 can go inside, and the minus can go inside, minus 2, and you get that this is equal 1 over n squared, right? Now, this is true for every I. So the probability, if probability of each is less than that, probability that at least one of them will be smaller than this is smaller than n times this probability. This is called union bound. Let me show you. What does union bound tell us? So if this is a bunch of events, right? This is one event, that's another event, and so forth, and they might be overlapping. If they're disjoint, then of course the probability of the union is equal to the sum of probabilities. But if they overlap, then clearly probability to belong to the union is smaller or equal than the sum of the probabilities, because they partly overlap, which reduces the measure of the union. So if you have this probability smaller than 1 over n squared, the probability that this is true for at least one of them, so that it belongs to the union, is smaller than n times 1 over n squared, right? Which is equal to 1 over n. And so we have that the total probability is smaller than, let me show you here, the total probability is n times 1 over n squared, which is equal to 1 over n. And the other inequality is proved in a similar way, namely the scalar product of two vectors is product of their norms times product of the cosine of the angle. And because both norms are smaller than 1, if you drop the norm of the vector that is pointing to the north, you get that the size of the projection of the other vector is smaller than the size of that vector times the cosine of the angle. So now from the corollary that about belonging to a slab, right? We saw that the probability to get out of the slab, right? Namely that you are larger than c over square root of d minus 1, right? Probability to be outside of a slab of this thickness is smaller than 2 over c times e to the minus c squared over 2. That's the theorem that we just sketched. Its proof. So then you get, if you replace now c with 6 square root of 6 ln n, then you get precisely what you need for the theorem on the left. And here, if you replace c by square root of 6 ln n, you get here on the bottom, and you have to square it here. So it will be 6 ln n divided by 2. And of course, ln n, square root of 6 ln n is bigger than 2 when n is bigger than whatever, 2 or 3, some small number. And you get that this is smaller, this will be smaller than, sorry, it will be larger than 1, right? Or larger than 2. You can compute easily. Let's see, so you want square root of 6 ln n. You want it to be larger than 2. So you want 6 ln n to be larger than 4. So ln n, you want it to be larger than 4 over 6, which is 2/3. And so n should be larger than e to the 2/3. And this is, right, because this is smaller than 1, this will be smaller than 3. So for as long as you are taking at least 3 points, this will be smaller than 1. And then you have 1 over n cube. And now how many pairs of vectors you have? You have n choose 2, right? So for each pair, you know that the probability is smaller than 1 over n cube. So the total probability that at least one pair of vectors will be such that one is outside of the orthogonal slab to the first vector, that will be smaller than n times n minus 1 divided by 2, which is n chooses 2. and then times 1 over n cube, which is probability for each pair. And of course, this is smaller than, so this here is smaller than n squared. And when you multiply it with 1 over n cubed, this is smaller than 1 over 2n. So now the first property is preserved with probability 1 minus 1 over n. The second property is preserved with probability 1 minus 1 over 2n. If you multiply this, then both probabilities will be preserved with probability, both features will be preserved with probability of at least the product of the two probabilities. And lo and behold, if you multiply these two probabilities, you get, because this is positive, you get that this is larger than 1 minus 3 over 2 times 1 over n. So this is really all direct consequence of the Gaussian annulus and the slab estimation. What is the practical use of this theorem? It essentially tells you that if you choose n vectors, and number of vectors that you will choose will be always much smaller than dimensionality, because the whole purpose of this is dimensionality reduction, to handle this, what's called the dimensionality, high dimensionality curse, namely that doing anything in high dimensional space is extremely costly, right? Just because of the sheer number of dimensions, the algorithms usually scale exponentially with dimensionality of the space. So, and you will choose if this is of the order of 10,000, right? And in all likelihood, you will choose to be maybe between 100 and 1,000, depending on application. So it will be at least an order of magnitude smaller than D. And then if you choose these vectors using a Gaussian distribution to generate the coordinates, Gaussian distribution with the unit variance, then almost all of these vectors will be larger than 1 minus 2 ln n divided by d. And because you are, of course, picking randomly numbers within the unit sphere, length of xi is smaller or equal than 1, but larger than this. And this is almost 1. It's very close to 1, because if n is of the order between 100 and 1,000, then ln n is between maybe 10 or 20. So this will be, say, to be generous, 20 divided by 10,000, which is essentially negligible, right? So almost all vectors will have unit length, right? And lo and behold, their scalar products between any two of them will be smaller than this. And again, the same story, right? If, say, ln n is of the order of, say, 10 or 20, this will be 60 divided by, say, 10,000, and then taken a square root, which will be exceedingly small, which means that these randomly generated vectors are almost orthonormal. So they are ideal candidates to be used as coordinate system, which is precisely how this whole mumbo jumbo was designed, precisely for the purpose of using these randomly generated vectors as basis vectors to do projections onto them. So that is the first part. Randomly chosen vectors are very good candidates to make a orthonormal system. So now a little bit more, because our goal is to prove this Johnson-Lindenstrass lemma that in fact tells you that projections will in fact reduce the dimensionality. So as I said, just like in randomized hashing, you will use these random vectors, U1 up to UK, say K of them, to project your vector to these vectors. So this is now the trick. So all these vectors live in a vector space of huge dimensionality. But if you project one vector to say K almost orthonormal vectors, you can ignore their coordinates and use only coordinates in the system that is U1 up to UK, right? So essentially we are now projecting, so we have an almost orthonormal coordinate system. The vectors are almost orthogonal and they are almost of unit length. So now if I have any vector, I can represent it by its projections to these three in this case, three vectors. In this case, it will be, of course, onto K vectors. So we consider this projection. So let's see what we can tell about it. And this is the crucial lemma that is used in, that is essentially the kernel of the Johnson-Lindenstrass famous theorem. It says the following: if you choose randomly with just Gaussian of unit variance K vectors, and you consider the projection of your vector V to these K vectors, then the size of the projection will be almost equal to square root K times the length of your vector, because the probability that this is larger than epsilon times square root K. So you have your vector V, you project it to a few vectors, K vectors, right? Then you look at the projected vector, which would look something like this, right? Here is the projection. Then the length of the projection will be almost square root K times the original vector V, because the change of the how much you will err compared to K times square root vector V, the error will be, the fraction of the error, relative error will be smaller than epsilon. This will happen with a probability smaller than 3 times e to the minus c times k times epsilon squared. So epsilon is the bound, right? K is how many vectors you used for projection, and c is a constant independent of the dimension. It's this 1 over 96. Or can be actually made larger than that, but with a more complicated calculus. And the proof is direct application of the previous theorem because you see, you just notice that the scalar product of ui and v, namely the projection, is equal ui times vj, right? That's the definition of the scalar product. And all the vectors ui are Gaussian vectors with unit variance. And in probability theory, we prove that the linear combination of Gaussians is yet another Gaussian. So the projections will inherit the Gaussianity of the vectors themselves, right? And if we compute the variance of this scalar product, this will be the variance of a linear combination. So you can go inside with the variance because it's uij's, they are all independent Gaussian variables, right? So the coefficient, when it goes out of the variance, it gets squared, right? And the variance of each of these guys is just 1, so you get sum of the squares of vj's. And now notice, we can always take vector v to be of unit length, because in this inequality, if you can divide both sides with the norm of v. V is also a linear mapping. So if I divide by norm of v, this will disappear. This will be just an orthonormal vector v, right? And here the length of v will disappear. So this is obviously by linearity true of any vector, if and only if it's true of unit variance vectors, sorry, with unit norm vectors. So we can assume that norm of v is just 1. So the variance of the projections is also 1. So if you project your vector to randomly generated vectors that are generated with a Gaussian of the unit variance, the projections will also have a feature that they are Gaussian random variables with unit variance. So we can now simply apply the Gaussian annulus theorem just by taking beta equals epsilon times square root k, because if you substitute this in this formula, that is precisely our Gaussian annulus formula. If you substitute beta with epsilon times square root of k. Now you can slightly improve this projection by dividing it by square root k, right? So if you start with the inequality we just saw and you divide both sides with the square root k, so then this will disappear and this will disappear. Here you will get square root k, but this is precisely f star, right? Then you get that the length of the projected vector minus the length of the original vector will err more than epsilon in a relative error, with probability that is very small, namely smaller than 3 times e to the minus ck epsilon squared. Right, so that's the crucial inequality, namely this normalized projection of a vector will be of the same length as the vector itself, with error, relative errors larger than epsilon, larger than epsilon, with probability smaller than 3 times e to the minus ck squared. So we can, the direct consequence of this is this famous Johnson-Lindenstrass lemma, which is crucial for data science, right? Which says the following now. So for any epsilon between 0 and 1 and any integer n, if you choose k many vectors where k is sufficiently large, how large? K has to be bigger than 3 divided by c times epsilon squared times ln n. So notice the number of points is here figuring with the logarithmic factor that grows much slower than n grows. Then if you randomly choose your vectors by Gaussian with unit variance, the probability sorry, what am I saying? Forget about randomly chosen vectors. So the vectors that we used to produce the coordinate system, they were randomly generated. Now, these are arbitrary vectors. Then the length of the projection of the difference of these two vectors minus the length of the difference of these two vectors will be smaller than epsilon times the length of the difference. What does this mean? It means that the relative error of the difference that you made by replacing Vi minus Vj with the normalized projection, then the change in the size, you see, this is the idea. You have these two vectors, V1 and V2. And what you are concerned with is that after you project, this vector size of this difference remains unchanged or almost unchanged, because this would mean that points that were far apart will stay far apart. Points that were close will remain close. And this tells you that the normalized projection of this vector, which is difference of the two vectors, minus the size of the difference, will incur relative error smaller than epsilon, right? Because this difference, so f star of Vi, f star Vi minus Vj, length of this, minus length of Vi minus Vj, divided by length of Vi minus Vj, right, will be smaller or equal than epsilon, which means that the relative error that you incur by projecting this vector can change its length during this normalized projection only by a fraction of at most epsilon, for as long as the number of the dimensionality of the projected space is at least 3 over c epsilon squared times ln n. Right, so this is a tricky matter, so read it carefully at home. And it's a direct consequence of the previous lemma about random projections. You can verify it yourself simply because it's exactly the same argument as we did for the random projection theorem. It's again just counting how many pairs of vectors you have, what's the probability of shrinkage of each pair, and lo and behold, you show that probability of the shrinkage, this is straight from the random projection lemma, is less than 3 over n cube. There are n chooses 2 pairs, so that's less than n squared divided by 2 times 3 over n cube. You get, lo and behold, less than 1 minus 3 divided by 2n. So now, how do we use this theorem? This theorem is really it's, for example, typical example would be nearest neighbor search. So imagine that you have a bunch of papers, a bunch of articles. You can represent them as vectors in what way? Well, you take your dictionary and for each word you count how many times it appears, right? Well, the size of your dictionary is likely to be, say, 100,000. So each vector, each paper will live in the vector space of dimensionality 100,000. So computing now, for each new paper as it arrives, the distances, right, Euclidean distances to all of these papers, it will be excruciating, right? Because each of these vectors is of size 100,000, right? Instead, what you do is you do the following trick. So this is what I just told you. So you choose the number of vectors, and you remember the number of vectors in the epsilon bound figured only as an ln. So ln 100,000 will be only 12, right? And so by the Johnson-Lindenstrass lemma, if this is by replacing C with 1 over 96, but one can get much sharper bounds using more subtle estimates. But you choose the size of your database and how many queries you are expecting. You compute K in this way, and K will be typically in the order of a few thousand. And then from this 100,000 dimension space, you will project all vectors only to, so you will pre-process your database by projecting all the vector to only these K many randomly chosen vectors. Then when a new article arrives, you will project it to only K many vectors, right? Rather than the size of your database that can be also in tens of thousands or in hundreds of thousands. You project them only on these K many vectors, and you then look for the nearest neighbor in the projected space. But projected space is of much smaller dimensionality, so nearest neighbor search, even exhaustive, not approximate, but exhaustive nearest neighbor search will be much, much faster than if you did it in a vector space of size 100,000. And lo and behold, this Johnson-Lindenstrass is implemented in database systems that are designed to deal with vector spaces of extreme dimensionality. And besides this dictionary business, the main application is for something called microarrays in genetics, where the dimensionality is again in the orders of hundreds of thousands, because it corresponds to various combinations of genes. I'm not familiar with that, but it results in a very high dimensional space. And so the software that does then, if you want to cluster, for example, you see for another application, it's clustering. If clustering in extremely high dimensional space is extremely hard because the distances are hard to compute. But if you project in a vector space of dimension, say 3000, then clustering works much faster than in a vector space that is of dimension 100,000. And because of Johnson-Lindenstrass lemma, clustering in the projection will be correct because with high probability, things that were apart in high dimensional space will stay apart in the projections, and things that were close in high dimensional space will stay close in these normalized projections because the relative error is relatively small. So probability that you will misclassify something will be small. So this is another example of this brilliant technique of random projections. So I suggest the following. So read randomized hashing, and then read these notes carefully, and it won't kill you. You know, even you can read the mathematics, is just simple algebra. And make sure that you understand what is the essence of the theorem, namely that the whole business here is to reduce construction in high dimensional space by something that is almost as good in much lower dimensional space where everything runs fast. So if you do data science and you see that you are applying Johnson-Lindenstrass, this is just a pre-coded, usually in C++ function, and you can know what it does. That it does projection on randomly chosen vectors that is with high probability. These vectors are orthonormal, and the projection almost preserves the distances. So doing nearest neighbor search or clustering in the projected space will be as good as doing it in this unmanageable space. Okay, so as I tell you, look, computer science is gone out of its infancy. And what you see now in this class is what modern computer science looks like. Unfortunately, it's full of statistics and mathematics because it became, you know, you cannot make in your garage a rocket to go to the moon. So if you have to handle gigantic data, you have to use a sophisticated methods, and randomized hashing and Johnson-Lindenstrass are prime examples how randomized methods are used to deal with gigantic data with high probability in a highly accurate way. Yeah? So please read this carefully. In the exam, you will be asked only, you will be tested only the understanding of what these theorems say, not their proofs at all, but just you will be tested on what the meaning of all of this is so that you can use it competently in your job if you end up doing a job of a data scientist. Okay, so now we will make a break, a 5-minute break, and then I am giving the microphone to Jojo, who will, am I pronouncing your name correctly, Jojo?
Yes, yes, Jojo.
So then she will pick it up from here. Jojo is a new faculty member at CSE who has just recently joined, and she's an expert in computer security and social networks. So very practical things, and she will pick up the lectures from here, but I will keep my office hours. Oh, today we have a meeting in the school, so I'll postpone the office hours for tomorrow, most likely. I'll send you an email. We have the dean is giving the townhouse speech about restructuring of the university, so we all have to see what awaits us. But I will keep my office hours, and Jojo will also have office hours, I assume, when you can ask her questions. So we will both be available to you. Okay, so Jojo, let's get a 5-minute break and then you pick up. How does this sound? Oh, let's try. Can you share your screen now?
No. Can you please make me a
Okay, how do I do that? Let me see. Stop share. You know, it just doesn't, my Wednesday lectures do not show on the list for some reason. Let me just see here.
You can make me, a temporary co-host for this session.
Yeah. Let me see. Multiple participants can share simultaneously. So how do I do advanced sharing options?
Yeah, I can share my screen now.
Excellent. Very good. Okay, let's just make a short break for you guys. You were bombarded with heavy duty random stuff, and we need a little bit of breathing. Okay, so Jojo, why don't you go ahead?
Sorry, I was muted. Okay, thanks, Alex. So I'll pick up from today's lecture. I'll start from SVD, the singular value decomposition, because hopefully I can finish this topic in 1 hour, hopefully. Okay, so before we talk about the SVD decomposition, I would like to have a brief review of PageRank, because in PageRank, can you see my screen here on Overleaf?
Yes.
Okay, cool. So in the previous couple of weeks, we talked about PageRank. So in PageRank, we talked about eigenvector and eigenvalue. But when we calculate eigenvector and eigenvalue, we are actually working on a square matrix. Okay, but so by solving this equation, AX equals to lambda X. So X here is a vector, and then you can get the eigenvector and the corresponding, you can get the eigenvalue, which is lambda, and the corresponding eigenvector. Okay. And also we need some some fundamental linear algebra, which will be used for today's lecture. The first one is actually, Alex has just talked about the orthogonal vectors. So if we have 2 vectors u and v if these two vectors are orthogonal to each other, and then the you may say the inner product or the dot product or the scalar product, it has different names. Well, the product is equal to 0. Okay, so this is the definition of orthogonal vectors. The second fundamental tool that we're going to use is the projection of vector u on a vector v. Okay, so the projection is a scalar. Okay, so the projection of u on v is defined as here. So the inner product of u and v divided by the length of v. All right. The SVD decomposition, okay, and so corresponding, or compared to PageRank, it works on the eigenvector and eigenvalue. It works on a square matrix, but for SVD, the matrix we are going to decompose is you may say non-square matrix. Okay, so the dimensions of A is here we called n times d. Okay, so after the decomposition, we will get three matrices. Okay, so we will get U times D and times V transpose. And those are the corresponding dimensions of these three matrices. Okay, and then the vectors in U, in matrix U is called the left singular vector. Okay, so the left singular vectors u1, u2 till ur. And the vectors in V is called the right singular vectors from v1 to vr. And in the matrix D, so matrix D is a diagonal matrix consisting of the singular values. Okay, so these would be the decomposition result of an arbitrary matrix A. Okay, so now let's move on to the slides for SVD. Okay, so before we introduce SVD, we have sort of a motivation problem here. Okay, so this is the problem. Assume we're given endpoints on a space. Okay, so endpoints are A1, A2 till AN. So each point A is a vector in a space. Okay, so the problem is that we wish to find a line. Okay, and we use the vector V to denote this line. We wish to find a line which is the closest to all of these points, all of these endpoints, which means that we try to find a line that the sum of the squares of the matrices. Okay, so the sum of the distances from points A to the line V is minimal. Okay, so this is the motivation problem. If we take a look at this two-dimension space as an example, so suppose we have 3 points, so point 1, point 2, and point 3. Okay, we try to find a line V, okay, to minimize the sum of the distances from the points to the line. Okay. Now, as we can see, let's take a look at this point AI as example. Okay, so the distance from point AI to the line V is denoted as this short green bar here. Okay, and the red bar is, as we can see, the projection of vector AI on the line V. Okay. All right. So according to the triangle theorem, we can get this equation. Okay. So the square of the projection AI on V plus the square of the distances between AI and the line V is equal to the square of length AI. Okay. Guys, if you have any question, please leave a question in the chat box, or you can just unmute yourself. All right. So, and then we can rewrite this equation and get the formula for distance AI to V. Okay. So we can get actually the sum of the square of the distances is equal to the sum of the length of AIs minimize the projections, okay, the squares of the projections, right? Because as we can see, the points A1 to AN are given, okay? So those are given points. So we can say that the sum of the square of length AIs is constant. Okay, so the problem, the motivation problem of minimizing the sum of the distances is equivalent to maximizing the projections. Does that make sense?
Yeah. Is this like similar to like when you're trying to find the linear regression line in statistics?
Linear regression. Yeah.
Okay.
A bit similar. Yep. Okay. So now we can find an equivalent problem to this motivation problem. All right, let's move on. So if we change from, because in this motivation problem, we're trying to find a line, okay, with the minimal distance to the given points, but we can also try to find a subspace, okay, change from a line to a subspace, okay. So the previous problem not only applied to lines, but also applied to subspaces. So the problem becomes minimizing the sum of the squares of the distances of a set of points to a subspace is equivalent to maximizing the sum of the squares of the projections of the vectors corresponding to these points to onto such a subspace. Okay, so we just change from lines to subspaces. Okay. Now, okay. So in the previous problem, we're just given n points. Okay. So suppose that each point is with the dimension d. Okay, is with dimension d. And now we can use a matrix to represent these endpoints. Okay, so just like what we have here, okay, so we have a matrix N with dimensions n times d. Okay, so we put all of the vectors A1 to AN into a matrix. Okay, and in the matrix A, so each row is the transpose, AI transpose of the vectors AI. Okay, does that make sense to you? So for each AI, it has dimension D, and we write all of the AIs into a matrix, and then we get a matrix with dimensions n times D. Okay, so we have n points, and each point is in dimension D. Okay. Now, if we use vector V to represent an arbitrary vector of a unit norm, So unit norm means the length of the vector v is equal to 1. Okay. So as we given in the fundamental tools, the projection of vector u on vector v is in this form, given in this form. Okay, the inner product of uv divided by the length of v. Okay, now if the given vector is a unit vector, the length of v is 1. Okay, so if the length of v is 1, then the projection is equal to the inner product of u and v, right? So that's why we get this equation. So the sum of projections ai on v, the sum of the squares, okay, becomes the sum of the squares of the inner product ai and v. Okay, so as we know, ai in matrix A, each row is a transpose of vector ai. Okay, so this sum is actually equals to this value. Okay, in the matrix A times V, the length to the length of square. Do you guys understand this part? Any question here?
Are the vectors like represented in column first, and then you transpose it so that it becomes a row?
Yes, yes.
Oh, okay.
Yeah. So A for yeah, as we state here in matrix A, each row is a transpose of AI. Okay, so actually for the inner product, you can rewrite it as AI transpose times V, right? And then you can get exactly A times V, the length square. All right.
Yep.
Okay, so now you see, after we sort of model the problem, okay, so given us this problem, we have sort of project the problem into equivalent one to maximize the projection, okay, the square of the projections. And now we get the very neat equation for the projection. Okay, now we can probably try to solve the original problem. So what do we do here? Right. So the original solution, okay, the solution which is the best fit line is given by a vector. We are trying to find out this vector, okay, or the line or the subspace, okay, is given by a vector v for which this value AV, the square length of AV is maximized. Okay, so we are trying to find out this vector v. Okay, and then we have our first definition here. So we define the first singular vector of v to be vector v1. Okay, so just like in eigenvector and eigenvalues, you may have multiple eigenvalues and the corresponding multiple eigenvectors. Okay, so here we have our first singular vector defined as v1. Okay, so the first singular vector v1 is calculated from this problem. Okay, so v1 is equal to the argument of maximize the length of AV, satisfy that the length of V is 1. So V is a unit or a unit vector. Okay. So after we find the first singular vector, we can calculate the first singular value. Okay, so the first singular value is defined as, so sigma 1a is equal to the length of AV1. Okay. And later we will talk about an algorithm to find out the first singular vector and the first singular value. All right. So these are the definitions about the first singular value and the first singular vector. So what about the second singular vector and values? Okay, so after we find V1, we can find V2 defined as, okay, argmax, the length of AV. So we try to find V, satisfy that the length of V is 1 and V is orthogonal to V1. Okay. If we can find this V2, then we can get our second singular value. So sigma 2a is equal to the length of A times V2. Okay. And then recursively, you can get the kth singular value and the kth singular vector. Okay, for example, Vk is equal to argmax, the length of AV, V, such that the length of V is 1 and V is orthogonal to all of the previous singular vectors from V1 to Vk minus 1. And we get the corresponding singular value. Okay. So we will continue to find all of the singular values and vectors until we reach a number R, satisfy that we can only find a vector. So we can only find a vector V that the maximum of the length AV is equal to 1. Okay. So which means we will continue these steps to find V until we couldn't find any vector that the length of AV is greater than 1. Okay. So this equation means, so for so in this formula, all V satisfy the condition that the length of V is 1 and V is orthogonal to all of the previous singular vectors. Okay, and we will see that actually V is one of the solutions to the equation AX equals to 0. Okay, because if the length is 0, so which means all of the elements in A times V is 0. Okay, so we can see that V is actually one of the solutions to the equation here. A times X is 0. Okay. The solutions for this equation is also called the kernel of A. Right? And then we have our first theorem here. So for all K is in a range of 1 to R, then the subspace Vk spanned by the vectors, spanned by all of the singular vectors from V1 to Vk is the subspace, which minimizes the sum of the squares of the distances of the points given by the vectors corresponding to the rows of A to a k-dimensional subspace. Actually, this theorem is the same as the problem here, okay, or the solution to the problem here. But we sort of reform the problem into a matrix format. All right.
Yeah.
Yep.
In the previous slide, in the second last line, what do you mean by we break the ties arbitrarily?
Say it again.
What do you mean by we break the ties arbitrarily?
Here.
Yeah.
Okay. So as long as you can find a V satisfy this condition, which means as long as you can find a V with the length of V1, V equals 1, and you can maximize it, because you may find many. Okay, as soon as you find one, you can break it.
Yeah. Okay, thanks.
Yep. Yeah, it's good. So if you have any question, just unmute yourself. All right. Yeah. So you see, our original problem is, given us endpoints, we try to find a line to minimize the sum of the distances from the points to the line, and then we generally and smoothly move from the problem into a matrix-based problem. Okay, and we made our conclusion, or conclude our first theorem here. Okay, now, so we can see for the first singular vector v1. So v1 is a unit vector. Unit vector in the direction in which the unit ball. So that, what is a unit ball? Unit ball, obviously the length of the vector is equal to 1. Okay, and then for all of the vectors satisfy this condition, it will consist a ball in a space. Okay, depends on the length, the dimension of the vector. Okay, so we can get that V1 is a unit vector that in the direction of V1, the unit ball get maximally elongated. Okay. Yeah. So yeah, actually you can this result, or this conclusion, is exactly what we actually for V1 is here, is exactly what we defined for V1. So V1 is the vector in the direction that, the unit ball, so which means in this condition, AX, the length of AX is maximally elongated, and similar for V2. Okay. For this conclusion, okay, you can also prove that for vectors u1, u2 till ur, so u1 is a times v1. Okay, if you take a look at the definition of u1 and also the definition of singular value sigma 1. So sigma 1 is the length of AV1, right? And U is the vector A times V1. Okay. Later on, we will talk about the relationship between U1 and V1. Actually, you can see the relationship here. And why do we call left and right singular vectors? Okay, so you can easily prove that U1, U2, and UR, just like V1, V2, and VR, they are also orthogonal. Cool. Okay, as we defined the orthogonal vectors here, okay, because we see V1, V2, and until VR, they are all orthogonal. Okay, orthogonal to each other. So you can also easily prove that U1, U2 till U are also orthogonal. Okay, you can try to prove this after the class, and you can also send me or Alex your proof steps, and we can help you to have a look. Okay, so people may be wondering why do we have R here? Just like we defined or we reach to the number R, or the number of recursions here. So what is R? Okay, you can also try to prove that R is the rank of matrix A. Okay, you probably can find also find the proof in the textbook, or but by just Googling it. Okay, so let's further move on to other properties of the SVD decomposition. Okay, so first of all, so let's represent each row vector AI via its projections on the unit vectors VI. So what's the meaning of this sentence here? We represent AI by using VIs. Actually, if you imagine on a 3-dimension space, okay, you have an arbitrary vector. Okay, so the vector, let's say it has coordinates 1, 2, 3. Okay, so this vector can be projected on the 3 basic axes, I, J, and K. Okay, so the random vector or the arbitrary vector can be projected on the 3 axes I, J, and K. So similarly here, because as we know, all the VIs, all the vector VIs are orthogonal to each other. So AI can be represented by using vectors VI plus, okay, because as we see, we are in a dimension D space. So maybe we just have R singular vectors. So if we want to use VI to represent AJ, the vector AJ, we need to have another component, okay, plus a component in a direction X, okay, X is orthogonal to all VIs, okay, and then we can represent the vector AJ by using all of the singular vectors VI and vector X. Okay, here we use XJ to corresponding to the arbitrary row vector AJ. Okay, anyone have a question here? Okay, as you may still remember, so because VI, each VI is a unit vector, okay, with length equals to 1. Okay, so this inner product is also equal to the projection of AI on AJ on VI. Okay, so this part, and probably we can use the example here. Okay, so let's say we have vector A and vector B. Okay, so the projection of vector A on vector B is the green vector A1. Okay, and A1, the length of A1, let's say if the length of B is 1, and then the length of A1 is the inner product of A and B, right? and the direction of A1 is the same as the direction of B, right? So now let's get back here. So this part, the inner product of AJ, AJVI times VI. So this part is the vector of the projection AJ on VI. Okay, so now if you imagine on a 3-dimensional space, if we have arbitrary vector with length ijk, so you will have I in the direction of I, and j in the direction of j, and similarly k in the direction of k. Does this make sense to you?
Yes.
Okay, cool, thanks. Okay, so after we represent AJ by using VI and XJ, okay, and then let's move on. Okay, so this is very important because we know for all VI, okay, all VIs are orthogonal to each other. Okay, so we have A times, this should be a VI here. So A times VI is equal to 0. Okay, and each XJ satisfies AJ, the inner product of AJ XJ is equal to 0. So which means AJ is orthogonal to XJ. Does this make sense to you? AJ orthogonal to XJ? Nope. Okay. So as we okay, let's come back to this page, and you'll have a clearer idea. Because as we see here, all of the VIs are orthogonal to each other. Okay, and we cannot find any vector V which is orthogonal to all VIs, and so sorry, let's re-represent it. So if there exists a V which is orthogonal to all V1 to VR, and then V can only be a solution to AX equals to 0. So all of the V's, all of the vector V's satisfy this condition has to be a solution to AX equals 0. So which means for all V, A times V is 0. Okay. So that's why we have here. Okay. So because you see, X is orthogonal to all VIs. Okay. So which means X times, so the inner product of X VIs are all 0. Okay. If it satisfies this, which means A times V is 0. Okay, so if A times V is 0, or A times X is 0, and then every row times the vector X is also 0. Does that make sense to you?
Yes.
Okay, cool. That's cool. All right. So if this inner product is 0, so this part is 0, and then AJ will become, so AJ is equal to the sum of the inner product AJ VI times VI, right? So we get this equation. Okay, if we calculate the norm or the length on both sides, we will get this equation. Okay, the square of the length AJ is equal to this the sum of the squares, of the inner product AJVI. Okay, because we see VIs, they are all unit vectors. So the length, all of the lengths are 1. Okay, so we get this equation. Okay. But this is just for an arbitrary row vector in matrix A. Okay, so if we add up all of the row vectors in A, okay, so we will get the following equation. So the sum of the squares of the length AJ, okay, is equal to this part, sorry. Yeah, so sigma I from 1 to R, inner product AJVI is actually the square of the length of AJ, right? And then we swap these two sums. We move sigma I to the front and sigma J behind sigma I, okay? Yep. So because we see for the inner sum, okay, sigma J from 1 to n AJ times VI, this is exactly A times VI, right? Okay, so you will see this very familiar to you because the length of AVI is exactly the singular value, sigma I, right? So we see, so we will get this result. Okay, so sigma J from 1 to n, so which means the length of the row vectors in A is equal to the sum of the square of the singular values. Okay.
What does the capital A with the small arrow mean?
Sorry. This this should be A because sometimes we use the small arrow above a letter to represent it is a vector.
Yeah.
Okay. So it should be A, not an arrow there.
Okay. Thanks.
Okay. Yeah. And further, we can rewrite the left part of the equation, sigma J, the square of AJ, as this. Okay, because we see AJ is a row vector of A. Okay, so the length of AJ can also be rewritten as this. All right. And we see the right part of this equation is also the exact definition of the F norm or the Frobenius norm of a matrix. Have you learned the Frobenius norm of a matrix before? The F measure, sorry, the F norm. So F norm is defined as the sum of the squares of the elements in a matrix. Okay, the sum of the squares of elements in a matrix. Okay, so this, the right part is exactly the definition of the F norm of matrix A. Okay, so we can conclude that as we defined here. Okay, so sorry, the norm should be in terms of F norm, there should be a square root. Okay, so this is the square of F norm. All right, so if we substitute this equation to the above one, we will get this conclusion. So the F norm of matrix A, okay, is defined as the sum of the square of elements in matrix A by taking the square root. Okay, so this is equal to the square root of the sum of the square of the singular values. All right. So we can see we can easily calculate the Frobenius norm of matrix A. So we can get sort of the sum of the singular values of A. Okay, but later on when we try to design an algorithm to calculate the singular value and the singular vectors of a matrix, you'll find probably this property is very useful. All right, so let's move on. Sorry, time flies.
Wait, excuse
yeah.
me.
Yep.
In like the second equation, you have like the summation to D, but in like the third equation, you don't have it anymore.
Sorry, D.
Yeah.
Oh, here.
What happened to it in the third one?
There is a mistake here. This shouldn't be ij from 1 to n. This should be, you know, I from 1 to d and j from 1 to n.
Oh, okay.
If you, yeah, there's a mistake here. Sorry. Maybe I have to talk to Alex to.
I have to correct all these little bugs.
Yeah. If we write it in this way, which means A is a square matrix, okay, we have to use this expression.
Yeah.
Okay. That's very good. That's very good. You notice it. This tiny part. Okay. Yeah. So okay. Let's move on, and then we define vectors vi as the right singular vectors of A. Okay, and if we define ui in this way, ui is A times vi divided by sigma ia. If we define ui in this way, and then ui is called the left singular vectors. And why we call ui left, oops, what am I doing? We call ui the left and vi the right singular vectors. Okay, because if we move back here, we see A, after the decomposition, the SVD decomposition, U is on the left and V transpose is on the right. So we call the columns in matrix A as the left singular vectors, and the vectors in matrix V as the right singular vectors. Okay. All right. Okay. So similarly, you can also prove, because previously we have talked about that AVI, so A times VIs are orthogonal to each other. So you can also easily prove UIs are orthogonal to each other. Okay, and this is super important. Matrices, okay, because we see, so sigma is the singular value, ui is the left singular vector, and vi is the right singular vector. Okay, so these can you tell me, is this a scalar value or a matrix? This result. sigma I, ui, and vi transpose. What's the dimension of this? Oh, sorry, forget dimension. Is it a scalar value or a matrix?
Was the singular value a vector?
Or matrix?
Oh, okay.
Okay, never mind. So sigma I is a scalar value, right? It's just a singular value. Ui is a vector. Okay, so ui is, can you tell me the dimension of ui? It's n times 1, right? Because u has n rows and r columns. Okay, and we have u1, u2 till ur. So the dimension of ui is n times 1. Okay, and the dimension of vi is again n times 1, right? So actually this is, hang on, did I make any mistake here? No. So this is a matrix. Okay, so that's why we call here the matrices sigma I, ui, vi transpose, the principal components of matrix A. Okay, and we will we will have this theorem or this result, and A, the original matrix A can be rewritten as this. Okay, can be rewritten as sigma I from 1 to R, and then sigma I times ui times vi transpose. Okay, guys, we will stop here. It's already 1 o'clock. Right. And next week, we will talk about how do we prove this theorem and how do we use this theorem in few applications, like how do we use SVD to rank web pages, and for, you may say, dimensions reduction and principal components analysis. Okay.
Joe, can you go back to like page 8?
8.
Page 8, I think. Oh, the previous page again.
7.
Yeah.
Okay.
Why do you square the a there in the third equation on
Square
no, the one where you have the sigma?
here.
No, it's to the right.
Here.
Yeah.
Why do we square sigma I, right?
No, why do you square the a?
It's not, it's again my typo. It should be
okay.
sigma I of A and then
like
in brackets squared.
Oh, okay.
Yeah, like this one.
Yeah, this is really confusing. I'll change it on the slides.
Yeah, that's all. Thanks a lot.
Oh, thank you so much. Sorry, I haven't got the pen and pad like Alex have, but I'll get probably by this weekend myself those tools. And next time I can draw stuff on this slide, make it more clear and easy to understand. Okay, thank you.